Good day, everyone. We're going to continue on our discussion of thermodynamics, and in this chapter, we're going to get into the heart and the real meat of the subject. We will return to chapter 16 after we do this one first, because I think it's important to get into the meat as quickly as possible, and I think it's an important chapter. In this chapter, we're going to learn about what the principles of thermodynamics are, what this subject entails, what it means. Um, we're going to revisit the subject of absolute zero temperature, which we mentioned earlier in the last chapter. We're going to go into more detail of what is meant by the internal energy of a substance, and we will clarify that as well. Within thermodynamics, there is going to be two laws that are principally important. One of them is the first, and the other is the second law of thermodynamics. We will talk about adiabatic processes, one in which there is no heat exchange. Those are important in certain functions of different types of engines, for example, and also in the atmospheric conditions of meteorology. And then we're going to talk about the meteorology in relation to the first law and what implications it has, and how we can understand things like why does the air get colder as you go to higher elevations. So that's the subject of what we're doing, and we will jump right into it in the next slide. Now, as this slide shows, the science of thermodynamics was developed in the early 19th century. It occurred during the period in which we saw the first steam engine used for railroad travel and the development of an engine that could replace horses. And as this was being developed, it was clear that in order to improve the efficiency of these machines, one had to understand the processes going on instead of using purely a tinkering mode of playing with different parameters and seeing how we could improve without actually understanding. So this is how it developed. And also at that time, the atomic and molecular theory of matter was not well understood. So the thermodynamics used macroscopic ideas such as mechanical work, pressure, and temperature. We knew in some way that heat flow occurs from hot objects to cold objects, and we knew that temperature was related to heat, but we didn't really, or heat transfer, but we didn't really have a good idea of it. The foundation of thermodynamics are based on two laws, as we showed in the last slide. The first law we will show uses the conservation of energy principle. And the second principle or cornerstone or law of thermodynamics is the fact that heat will only flow spontaneously from hot to cold and not cold to hot. If you want to make the heat flow from from a colder object to a hotter object, you have to do work on the system. It will not happen on its own. And so one of the principal applications of this is air conditioner, where we in fact make heat in a 80-degree temperature house get transferred to 90-degree outside temperature. That will not happen by opening the windows, which would of course just make the house hotter. So we'll study these and other events as we go through the chapter. Now, one of the principles that we discussed in the last chapter was that there is a lower limit on which the temperature of a mass of material it can have its temperature reduced to. And basically, we demonstrate that or explain that by saying or explaining that the temperature of an object is related to the kinetic energy, or the 1/2 mv squared of the molecules that are floating around in a jar. That jar could be a gas of material, it could be a liquid of material, but there is kinetic energy motion of the molecules. And as you lower the temperature, that kinetic energy becomes smaller. There is less 1/2 mv squared. As to say, the molecules start moving more slowly. Therefore, they bang into the walls with a much lower pressure. And the weight of the cylinder shown here eventually begins to uh, uh, fall down, and the gas is compressed into a smaller and smaller volume until it would reach absolute 0 degrees, in which case all of the kinetic energy has been reduced to zero. And in this case, where we're talking about a gas, which is shown in the figure, the volume of the gas would be approximately reduced to zero volume. You can see that in going, for example, from room temperature, which would be well, not quite room temperature, I should say, looking at the temperature of gas at the boiling point, 100 degrees, it's about twice the volume of gas as minus 100 degrees. So this is the meaning of absolute zero. So the first important point to start with in the discussion of thermodynamics is the concept of internal energy of a substance. And when we talk about this, there are four components that all contribute and add together to make the total internal energy. And the four parts or forms of energy that a substance can have is the first one we discussed in the last slide. It is the kinetic energy of each molecule when summed up over all the molecules in the substance gives us the total kinetic energy of the gas. It is also the only part of internal energy that is related to temperature. So when we heat something up, some of that energy can and will go into increased velocity, molecular velocity. When we heat up a gas, for example, that increased velocity will cause the molecules to bounce off the walls with greater impact and or impulse, as we said in the earlier chapters, and that will tend to lift the cylinder higher, as you saw in the last slide. So that's one form of internal energy. The second form is due to vibrational motion of the molecules. So for example, if we have a sodium chloride molecule, for example, with one sodium atom and one chlorine, they are connected together by their electronic bonds, or the bonds of their electrons that are in orbit about the atoms. And there's an equilibrium distance between the two that they want to stay at in order to achieve the lowest potential energy. And the effect that happens as we add heat is that these atoms begin to move away from each other like stretching of a rubber band or a spring, and then they begin to fall back towards each other due to their attraction, and then they get too close again and they come back out. And this vibration motion is another form of increasing the internal energy of a molecule. And that does not affect the temperature. Similarly, the third form of internal energy is that atoms in a molecule, of which there have to be at least two, such as the one we talked about earlier, sodium chloride. We can also talk about water molecules. That each of the atoms in those molecules can rotate about their common center of gravity, or the center of the molecule. And that rotational motion is also a form of internal energy. It also does not increase the temperature. And then finally, the molecules can be compressed towards each other, which increases their potential energy because they will push back when the compression is relaxed. And that is a form of what we call the potential energy. So those four forms are what constitute the internal energy of a substance. So, having introduced the four channels that heat can affect the internal energy of a substance, we want to mention that only that portion of the heat that goes into increasing the kinetic energy, or the 1/2 mv squared of the molecules, will affect the temperature. If most of the heat goes into the other three forms of internal energy, then the temperature will have very little rise. And we say that substance has a very high specific heat capacity, such as in the case of water. It takes a lot of heat to increase the temperature by a little amount. Now, the opposite is true for objects with very low specific heat. It takes very little heat to increase their temperature by a given number of degrees. So the last point is that I want to make is that we will only be interested in changes in the internal energy of a substance as a result of heat being added to it or work being done on the substance, such as compressing gas. That's work being done on the substance, where in this case the substance is the gas. So now we're ready to discuss the first law of thermodynamics. And that law states that the heat added to a substance increases its internal energy. And as we said earlier, that increase in internal energy can go into one of four channels. Only the channel involving an increase in kinetic energy of the molecules will show up as temperature. And secondly, the work done by the substance will decrease its internal energy because it expends energy doing work, such as the case where if the compressed gas is allowed to, it has a lid on it, and the lid is allowed to move up, then the gas can do work on the lid to release that pressure, but at the expense of reducing its internal energy. So to some extent, then the temperature will in fact go down because the internal energy has gone down. So there's two ways in which we affect the internal energy with external external things done to it. One is by adding heat, which will increase the internal energy. But if we instead do work on it, such as compressing a gas, that will also increase its internal energy. And that's the equation in item number 4, where you see the change in energy is equal to the heat added plus the work being done on the gas. So either one of those will increase internal energy. I can compress the gas or I can add heat to it. Now, the reason why it's given in another form, which is shown in the text, is the change in internal energy, the final minus the initial, is equal to heat minus W, is because W is defined as the work done by the substance. So just as in the previous example, if I allow a compressed gas with a lid on it to reduce the friction of the lid is allowed to move, then work is being done by the substance. So in that case, change of energy is internal energy is the heat added minus the work done by the gas. If, on the other hand, we do work on the gas, then the change in internal energy is written as Q plus W, and it's important to keep that in mind. Also, adding heat or doing work, either one, will increase its internal energy, and taking heat out of the substance will lower its internal energy. An important implication of the first law of thermodynamics is that if instead of adding heat, we do mechanical work on the system or the liquid or the gas, we can expect an increase in internal energy, and there will be a corresponding increase in the temperature. One example is rubbing your hands together to make them warm. I do work on my hands. I overcome friction by doing the work. That work causes the skin of my hands to get warmer. an important experimental measurement of the of doing work on the system to raise its temperature was done by the physicist named Joule. Obviously, we have the unit of energy named after him, but as you can see in the apparatus, by attaching a weight with a lever, with a pulley, and a system that can rotate the paddles of water, if I allow the heavy weight to drop down by a certain over a certain height, then I will have lowered the potential energy that has been released by the weight going down will be uh, transferred to the rotary motion of the paddles in the water. And doing that, we can heat up the water by doing mechanical work on this liquid. And one important result that came out of this was that by doing an amount of work equal to 4,180 joules, acting on 1 kilogram of water, raised the water temperature by 1 degree. So this allowed us then to get our first measurement of specific heat capacity, which basically says that if I've added a form of mechanical energy of 4,180 joules, then I will increase the temperature of the water of 1 kilogram by 1 degree. So here is one of the first questions that we have for this section. We are looking at the example of pumping air into a bicycle tire, for example. And as I pump on the handle of the tire pump to compress the air and push it into the tire, I have done work on the air molecules of the pump from the pump by compressing the air. That is to say, I've done work by making the air molecules come closer together as a result of doing work. And therefore, I have increased the internal energy. Because remember, there's two ways to increase the internal energy. I can either heat up the air in the tire, or I can do work by compressing the air. So in either case, by increasing the internal energy, some of that internal energy will go into increasing the temperature, the kinetic energy of the molecules, and therefore will increase the temperature. Now, here we come across the concept of an adiabatic process. The adiabatic process is one in which there is no heat that enters or leaves the system during the period of time in which we alter it. That could be to say that we either do work on the gas or we allow the gas to expand and do work on the lid of its chamber. Now, these adiabatic conditions are achieved by either thermally insulating the system from its surroundings, so there's no heat transfer, or doing it so quickly that there's not insufficient time for heat to enter or leave the system. And this process is very important in a number of areas. We'll continue with this on the next slide. This slide shows the example that we talked about in doing the multiple choice question a few slides earlier, namely the compression of air as we increase the number of air molecules into the tire of a bicycle using a pump. When this is done, we do work on the air by compressing it and pushing the air molecules closer together inside the volume of the tire. By doing so, and because we've done work on the air, which is in this case the system, then the internal energy of the system of air molecules has been increased. Therefore, there will be some increase in temperature as a result of doing this. But in this case, we can increase the internal energy by doing work, not by adding heat. This slide indicates a simple example of what happens when you uh, fill your mouth with air, with what we would call puckered cheeks, and we blow it through a very, by making the mouth opening as small as possible and forcing the air out onto a hot substance. For example, if you've burned your finger on the stove, you might try to cool it off by puckering your lips and or your lips and your cheeks and forcing the air out through a small size hole in your mouth. And as you do that, you expel a rather high pressure of gas that has been forced out of your mouth. And so in doing that, pressurized air begins to expand, pushing out the stagnant air molecules in the room, and therefore those air molecules from your mouth have done work on the surrounding air by pushing them further out. That makes the air from your mouth expand as it leaves your lips, and therefore it loses, since it's done work on the surrounding air, its internal energy has gone down, and therefore so has its temperature. In this last slide for the lecture, we can see a similar effect as what we just talked about with the air leaving the mouth or the lips, it expanding and causing the cooler air to the air out of your mouth to become cooler. The same thing happens in a pressure cooker, where there's a narrow jet of steam that's allowed to escape through the top uh, of the cooker. And when this does, or when this very hot steam comes off of the cooker, it will expand by pushing the air, the stagnant air around it further away, allowing the steam to expand. And as it expands, work is being done by the steam on the stagnant air, so that the internal energy of the steam goes down, and therefore its temperature also goes down. This is an exact analogy of what happens, or a similar case of what happens when you pucker your lips and blow air through the very small hole formed by your mouth when you force a volume of air out from it. Okay, so when we start up next, we'll go on to meteorology in the next lecture and resume from there.